All right, so this week, this is a short week, week 7. So in class, we're actually going to build a cable. I haven't yet figured out how to do that out of class quite as effectively. Um, so we're going to look at some of these items. So this week, there's a couple of things due. There is reading. There are 2 lab simulations. So we're looking at traceroute, which is another interesting tool, which is really a stacked set of pings, efficiency of our network, and then we have our quiz as normal. On the discussion board side, there is a request to look at these podcasts. And so this podcast that I picked a group of is from the TWIT, This Week in Technology group. So there are a lot of different types of podcasts here. If you would like to find another technology podcast and use it, you are also welcome to do that. Just shoot me an email and make sure that it's something that's appropriate. All right, so this one's kind of interesting. I love podcasts. I don't know if you guys listen to them a lot while you're working out, driving, whatever, but I tend to throw on podcasts instead of music because I get tired of hearing the same top 40 songs, and I can only handle a little bit of Britney Spears on the radio. All right, so somewhere I have. So this week we're going to talk about network cabling, and one of the things that drives me absolutely crazy is some of the sets here and language. So bandwidth is often mistaken with throughput. So in a technical sense, bandwidth is actually the highest frequency that a cable could transmit on. But in this case, we're saying how much can we theoretically transmit. And throughput then says how much do we actually transmit during a given time. So all of these are called bits per second. And remember, we looked at that from a marketing standpoint, why they don't say bytes per second, because it would look much, much slower. So the other thing we tend to do is we round them off, because we know this would actually be 1024, but we round it off. And again, it almost sounds a little quicker because we're rounding that. So kilo means 1,000, mega then is a million, giga is a billion, and terabyte is really a trillion bits per second. So when we look at those are kind of our measures of how fast we can transmit data. So on our networks, and we've done in class, and you can do it on your own, the speedtest.net shows us how much we can download at any given point from a particular web server. And so most of those were in the several thousands of bits per second. But we have issues with every one of these signals. So when we put things, especially into a copper cable, that copper is subject to a lot of different noise flaws. So it makes more sense to think about them setting. So here's our cable here, and in the case of Cat 5, 6, 7, 8, there's 8 different cables in here, not 4, but the same principle applies. So as cables run side by side, they are subject to this crosstalk. In other words, the signal from this wire bleeds onto this wire. Well, you can demonstrate that yourself a couple of different ways. So if you've ever went underneath like a high transmission line at night and taken a fluorescent bulb and gotten it to light up just a little bit, that's that same type of crosstalk or induced voltage coming across. So we have a lot of things we can do to minimize those. We have EMI from things like motors, fluorescent lights, copiers. Microwave ovens are notoriously bad about being really, really noisy in terms of just shooting out all kinds of random radio waves and electromagnetic interference. So crosstalk. So signals on one wire go to a different wire beside it. And the longer they run beside each other, the more they can induce a current on that other wire. So alien crosstalk between two cables. And then we have the near end and the far end crosstalk. Because when we take this cable apart, we're going to induce elements that can cause either near end or far end. So they're relative to your position. So near end is by you, far end is at the other end of the cable or the wire. So when we create a cable, when we'll show you what it's going to look like, we untwist. And the twisting is one of those ways that we can get out of moving some of this crosstalk away. Because here you show them that they're laying side by side and they go a long distance beside each other. So it makes sense. The longer I have two wires parallel to each other, then the more we can induce crosstalk. However, so this is a visual exercise, and you don't have to think about it. So hold your arms out in front of you. Notice that they're parallel, right? So when they're parallel, you can think about, well, sort of parallel. Depending on how many sports injuries you have, you can induce current from one to the other. But if I can twist my arms up together really, really tightly, are they running parallel anymore, or are they getting closer and closer to a 45 or a 90 degree angle? So ideally, when we twist those, and you guys have a little advantage with that cable wandering around, notice that they're twisted very tightly. And if you'd actually look, you'd see that we're crossing at almost 90 degrees every time. And by crossing at 90 degrees, we're minimizing that amount of parallel. So the twist will actually help us with some of the crosstalk. So some of this is some words again here. So attenuation just really means signal loss. So that makes sense. We send a signal out on a wire. The further we send it, the less signal it's going to have at the end. It's going to lose strength over time. So one of the things we can do is we can amplify a signal, and we can send that signal back up again to its original strength. However, if we're just simply amplifying it, we're adding that noise that we've added. So if I look at this chart, we've got some kind of noise going on. And if I just amplified it, it would also amplify that noise. So we actually do on a digital signals, we do something called regeneration. So we take that signal, we read it, and remember that signal is just zeros and ones. So 0, 1, 0, 1. We take that square wave, we read it, and then we resend it back out again. So it's called regeneration. Oh. So we think of electricity traveling really, really fast, and it does. However, it doesn't travel at the speed of light. And even if it did travel at the speed of light, you would realize that there's going to be some time delay based on the length of that cabling. So if I send a signal from here to England and back, it's going to take a little bit of time for that signal to propagate or to send and come back. If I send it to a satellite, and so now I've got a radio wave going to a satellite 22,000 miles above me in a geosynchronous orbit, and back, that's 44,000 miles it's got to travel. And you may have seen something about some of our landers that we've put onto various planets, including Mars. Some of those take 3 to 4 minutes for a signal to be back. And that's why the robot has to be self-contained, because we don't have enough time to control it in real time because of that length of delay. So latency, or that length, can cause us some issues. So if part of the reason we limit our length to 330 feet total is that idea of latency. If it goes over that on our network, then we've got to try some other technology other than just Ethernet and on a Cat5 or Cat6 cable, because we're going to get errors in the transmission. So cable length, what other things, what's in between it? Well, I said we regenerate that, but regeneration takes a little bit of time. So every time a signal hits something that regenerates it, it's got to read that signal and then regenerate it. So it takes some additional latency every time it hits a regeneration station. So if those packets then get treated slightly different and some go out faster than others, they arrive out of order. Now, if it's an email, that's not really a problem, because an email, we can take our time and they can reassemble it in order. But if that's a streaming video that you're doing, or you're doing a Zoom session or a phone call, then you can actually end up with some weird hiccups because you're streaming those out of order. The computer's going to try to put them back together in order, but some of them might be so late that it creates an issue. So latency, or how long it takes to send something, and so we have another term, this round trip time, so RTT, how long it takes to go to the destination and then back. So we're gonna see that in just a second, what it looks like. And then we have a couple of other settings in here and different communications models that we need to look at. So full duplex, so this is like your telephone. You can talk and listen at the same time. That makes sense. I can talk and I can hear. But if you've ever had to use a walkie-talkie, can you both talk at the same time on a walkie-talkie? No, you have to pause, wait for the other person to say something. So full duplex, we can send and receive both directions. So that's the fastest mode of communication. Half duplex says we can only send or receive at the same time. So a little slower, and we've got to come up with some model to know who should be talking and who shouldn't be talking. And then simplex means, a lot of times we call that unidirectional. That means we're just sending it out to everybody. So that's like a radio station. Everybody can get it, but it only goes one direction. So one direction and not the band. No, please no singing. My kids love One Direction, and I hear every song they've ever heard. All right. I should. Now, I will say there's a couple of James Arthur songs they've found that I like too. So sometimes they're decent. All right. So in here, this is a typical properties box. And notice that we can do a lot of different things. So we can actually set it to be 1 gigabit per second full duplex. Or we can let it auto-negotiate. So each network card will send packets to try to figure out what speed they want to go to. So whether it's half duplex, full duplex. So we can actually set this card all the way back to 10 megabits per second if you really needed to. And so maybe there's some intervening network connection issue, and maybe that's what we have to do. So that's what some of those properties. Most of the time, you don't ever have to mess with it. They're set to auto-negotiate. Boom, we're good. The one that is a problem, we don't really highlight here, but it's that power management. And so in a lot of settings, we've got power management where it turns off the network card. Well, you've got some kind of server client thing going on, like an ERP piece of software, and you want to go turn off that power management because it'll just drop that connection and then it won't relog back in easily. Oh, here's where we get a little more interesting. Multiplexing. So it would be nice if we could run a set of wires or 8 wires to everything out there in the world. But that doesn't always happen. And so if I think out in the country, and you think back to 1950s and 60s, and they're putting in phone lines finally, could they afford to run a wire to every house individually? In town, could they do that with thousands of homes? No. So we started coming up with something called multiplexing. So multiplexing really just says, I'm going to put multiple signals on one cable. Well, you've grown up and you've had that all your life. You just didn't realize it. So when you get a cable TV channel on the old style cable, remember that had all those different channels on it. They were shoved onto one connector. Well, that's what we're doing with a lot of our communications is we're using multiplexing to try to put multiple signals onto a single set of wires. So out in the country, a lot of places out here, even out in this country, they have what are called Slick 96s out there. And you can put 8 to 16 phone calls on a set of wires because they multiplex them together. So they create subchannels. Well, that makes sense. We're going to have little pieces. And we also call them the multiplexer a MUX. So sometimes you'll see that term. And a demultiplexer. So we have to figure out a way to put multiple signals on one cable, and then we have to figure out a way to take them back at the end. So copper, we have a couple of different ways we can send them. So the easiest way is time division multiplexing. Ooh. So time division says we divide it up equally. So if we're trying to send 4 different signals, each signal gets a second, and then the next signal gets another second. And so it's just broken up into equal sized chunks. So that makes sense as an easy way to do that. But what happens if only one of those channels really has all the data? Then the other 3 are sitting there just blank, not sending any data, while one is getting further and further behind sending it. So one of the other ones we came up with was something called statistical time division multiplexing. And so that assigns time according to both priority and need. So you could have a high priority communication channel and a low, and it would send that based on previous existing data, which one is statistically more likely to need data. So the other one, and a lot of you have seen this, you just didn't realize it, is frequency division multiplexing. So if you have DSL at your house, so you've subscribed to Windstream or somebody else who does DSL, you've got this idea of frequency division multiplexing. So here's your voice channel here, and up above it, you transmit data at the same time. And if you remember or ever had those little filters they made you put in every line you put on a phone, if you didn't, you'd hear this horrible squawking and squeaking in the phone line. And that filter just peeled that off so you didn't hear it when you're trying to do a voice call. So method 1. So we also have fiber optic cables. And fiber optic cables can also do multiplexing. So there's a lot of different ways we can do it with fiber optics. So one of them is we can have different colors of light or different frequencies of light. So there's not enough fiber in a lot of places to go around. So typically we'd have 2 fibers, one going out, one going in for each connection. But for example, at the courthouse connecting to the new jail that they built down in Fall City, there's not extra fibers they could lease from the phone company. So we used a combination where we set at 1350 for nanometers per second for one and 1550 for another, a different wavelength. So they didn't interfere with each other, and we could send them on one fiber instead of having to do 2. Well, now we've got even more capacity coming out because of something called dense wave division multiplexing. So we are now able to send over a fiber optic cable, in some cases 250 or more different channels. So we don't have to replace the cable, and we can just expand its capacity. So there's not as much fiber as you think going around the country. Most of the big fiber developments, so Level 3 that's now part of CenturyLink built out a network that actually goes right through this area. They have 144 fibers in the ground, which is a big fiber. But before we could only send one signal each way, that'd be 72 pairs. But now with dense wave division multiplexing, we can send tremendous amounts of data on there. So coarse wave division is a little cheaper, a little easier. So that means we're just spacing those channels out fairly equally, but not as tightly packed. So dense wave division is a little more expensive to implement. Both of them actually use something called a fiber Bragg grating. You're like, what is a fiber Bragg grating? So remember in science class at some point you got a prism and you could take light and break it into a rainbow? Well, that's essentially what a fiber Bragg grating does, is it breaks light up into its different frequencies, and then you send it down a fiber optic cable. So here from a telecom store is some of this equipment. You can go out and look at it and buy it yourself. So there's an 8-channel multiplexer. There's a 16-channel. So you can also look at the dense wave divisions if you go to some of these stores. And you'll see that you're going to spend a pretty good chunk of money to do it. But it's cheaper than the $50,000 to $100,000 a mile it is to tear up the ground and throw fiber optic cable in the ground. So one last one we use, and if you're getting served by Spectrum or Comcast or whatever name we're using for some of these cable companies, you're getting your signal, in most cases, off of a coaxial cable. It only has one conductor in the core and then a ground. It's one wire. And if you look at what we're going to talk about here in a little bit, where we've got 8 wires, what's the advantage to this? Well, there are a couple. I can actually send it over coaxial cable much longer without losing signal because of that giant piece of insulation in there. It isolates it a lot better, but it's old school. And there are coaxials much bigger than what you see coming into your TV. The one of your TV is about 1/4 of an inch. They make them up to about 1.5 inches in size, but they're hard to handle, they're hard to deal with. So we really have kind of moved away from that. The cable companies are still using it because it's already in place. Hey, let's figure out how we can do it. This is what we primarily use, twisted pair cabling. So 8 wires, 4 pairs. Usually there's a plastic sheath around it, and the wires are twisted together. So that twist eliminates that, or as much as we can, eliminates the wires being parallel. So the higher the frequency rating of a cable, the tighter those twists are. So there's usually an outside sheath. The cabling we're bringing out and showing in class is actually Cat 6, and there's actually a spleen that goes down the middle that actually holds the cables in a little better. Also is a little more of a pain in the butt then to deal with when we have to do it. So this cable, 4 pairs. So fast Ethernet or 100 meg per second connection uses 1 pair to send, 1 pair to receive. So we've got 8 wires, it only uses 4 of them. The newer gigabit style networks, so we're sending 1 gig per second, use all 4 pairs or all 8 wires. Well, here is a problem that I've ran into repeatedly. When you go into a large building, when they did these cable installs, they wanted to save money. And they said, well, that twisted pair only really uses 4 of the 8 pairs. So they repurposed 4 of them for things like phone lines. Oh, well, okay. And it worked. 100 meg per second connections worked really great. And then we went to plug in gigabit or higher connections, and all of a sudden it doesn't work at all. Like, why? Oh. So it involves a lot of rewiring when people took that shortcut to do that. It made sense at the time, they saved money. Doesn't necessarily save money in the end. All right, so there's a lot of different numbers in here, and really what they refer to is how fast a frequency we can send, and so they've got some different standards. Right now, I would probably not worry about anything besides 6 or 6E or 6A or 7. Cat 5 actually works. It'll do gigabit speeds, but at some point when we want to deploy 10 gigabit, it's probably not going to work as well for us, although on really short runs, it actually does work. But the cost difference isn't a whole lot between the two of them. We also have a data cable that looks very much like this, except it adds a shield. So this is what we're going to make a Cat 5, Cat 6. And notice it's got writing on it, tells us all about the cable. Cat 6 or Cat 5 with a shield on it, notice what it does. It wraps it with an additional shield, and it has a braided copper little shield on it, just like the coax are very similar. And we can use that in noisier environments. So things where we've got going by a lot of motors, or you're in a factory and you have a lot of electrical noise. You have to ground that. It doesn't help unless you ground one end of that braid so it has a way to drain off. But now that we can put fiber in at the price we do, it's kind of usually it's cheaper to run fiber, and you don't have to worry about that electromagnetic interference at all. So this is the typical thing we'll use. So this shows a couple of different ones, and on the far right is that spline in the center. You can see it there. So there's both PVC, and then they say there's something called plenum grade. Oh. So let's talk really quickly about plenum and non-plenum. So the PVC is the cheapest. Plenum grade, so 1,000 foot of cable, pandemic notwithstanding, normally 1,000 foot of PVC cable is about $150. Plenum's about $250 for a decent brand of cabling. So it's more expensive to run the plenum. What that means is the plenum is designed to use in an airspace. So anywhere you're moving air. So if you look up, we use this ceiling in here to move air back into the air registers. So if there were a fire of that cable or it started melting, it would move that signal, or the smoke from that would go into our lungs. PVC has this horrible habit of burning and smoking and making cyanide gas. And in large enough quantities, cyanide gas can be deadly. That's what they used to use in some states had the death penalty using cyanide gas. The most common thing we think about is actually Germany and the World War II, where they were using it on prisoners. We don't really want to poison our environment. So in most cases, I say even if it's not going through what typically would be called a plenum, I'll specify plenum anyway. It's not that much more expensive, and it just removes that headache. If you're on a bigger job, people like the fire marshal and such will come by and specify and make sure that you're pulling non-plenum cable in a lot of cases. So it's just an additional feature to make life a little safer for the rest of us. All right, so we're going to compare them. And it sounds like we're comparing something horrible. Comparing STP to UTP. So shielded and unshielded. I will say this, I almost never use shielded cabling because at this point we can run fiber. The only place that I see it used is weirdly when people are connecting microphones and things to radios is when they'll use that. So shielded is more expensive. They both spend or can share the same amount of data. So they both have the same length. They both can send at the same speed. You have to have specific ends. You have to know how to ground them. And they're harder to actually connect. So you've got some disadvantages, and the cost really, in most cases, says, hey, let's get a fiber and put it in there. And fiber used to be very expensive. It's gotten much cheaper. And now you can actually buy pre-terminated fiber because the terminations is the expensive part, and you can a lot of times pull that for an equivalent cost. So how do we use those cables? We got 8 of them in there. Well, there's a group that says TIA EIA has 2 methods. Oh, great. So we call them 568A and 568B. As long as we're using the same terminations on both ends, we can use either. If we don't, if we get confused because we use an A on one and a B on another, we actually might create some issues on our network. So we need to terminate them correctly. We can add noise that way, and we need to make sure that we specify the same connection on both ends. So one of the things I hope everybody takes out of here is that these color codes have a meaning. Almost always I've seen specified B. A has some legacy with the telecom industry, but as long as we have the same on both ends, we're good. So these color codes, and you can see them up there, are not that hard to memorize. And part of that is notice that we always do the striped cable first. So white, orange, or white, green lead off either with A or B, and then moves to the solid color. The only one that flips that around is in the middle, and notice pins 4 and 5 on either, both 568 and B are blue and white blue, blue and white blue. And those are the ones that are unused in just 100 megabit per second. Same with the white, brown, and the brown. And notice it's the same colors on both. So the only thing that really changes, if we look at this, see the fast Ethernet function, the white and the green and the orange and the white brown, they flip purposes here. That white orange and the white blue flip. So essentially, you can make a crossover cable by putting an A pin out on one and a B pin out on the other, and you can connect two computers without any other equipment. You're connecting the sending side of one to the receiving side of the other. So we call that a crossover cable. A straight through cable means we have all the pins on one side are identical. And even if you screwed up that color code, as long as you had both ends the same, it should work. Now, there's some other reasons why that presents some bad things, but for the most part, as long as you have the same pattern of pins on each end, they're going to work the same. Very rarely now you need something called a console cable. And a console cable is even different because it puts all the wires mirror imaged from each other. So it's a little odd. We don't typically use it. So here's that idea of that rollover cable where all the pins are just flipped from one side to the other. I can't tell you the last time I used a rollover connection, quite frankly. It's been a long time. If I were in a data center dealing with hundreds and thousands of routers, maybe, but I haven't used one in quite a while. Knock on wood. Now I'll probably have to build one this weekend or something. The other really neat thing that's happened with this, since these are electrical signals, we have figured out that we can actually put power out on our devices. We can use that to run devices on our network. The most typical thing we use are for cameras, access points, and phones. So if we have a VoIP phone and we have a PoE switch, so we don't need to actually plug it into a power supply. And these access points you see all over the ceiling out in the hallways, they don't have a separate power supply running to them because we just run it off of this idea of PoE, power over Ethernet. So older standard was only 15 watts. Newer standards are 25 or more. So we can run some of the newer higher powered access points. The other way you can do it, so if I don't have a PoE switch, I can actually run what's called an injector. So an injector says, so here I can see one on the bottom. That injector and here they're calling it a splitter, but it adds power. So our data comes in, and then it adds power and sends it out to the camera. So we can use those adapters if we need to. And so sometimes you have to weigh the cost. I'm going to put 2 devices that have PoE. Is it worth saving $400 and putting a non-PoE switch in? And so those are kind of the decisions. So that's what we're looking at for a device. And notice it's got both a power, and then it's got a side going in and a side going out. So that's what a power injector looks like. It's a lot neater to run them all into the switch, but again, if you only need 1 or 2 devices, that switch can get kind of expensive. All right. What other standards are we going to have to deal with? So fast Ethernet, we still talk a lot about because there are a lot of buildings that are only set up at 100 megs per second. Gigabit Ethernet for a lot of offices is something new. So we have some names for them that make some sense. So when you see this in a specification, and you see, all right, it's 100 base T. So 100 megabits, baseband signal, and it's twisted pair. That's what it really stands for. So notice that says 100 megs per second, maximum distance 100 meters, Cat5 or better, and it takes 2 of those 4 pairs. We move up to gigabit Ethernet, so 1,000 base T. So same thing, 1,000 megabits per second, baseband, and baseband really just means it's the only signal on those wires. We're not multiplexing anything in there. And speed is 1,000 megabits per second, maximum distance 100 yards or 100 meters, and Cat5 or better, so 4 pairs. And then we get up to where we're headed for a lot of offices, that is of 10 gig per second or higher. So 10 gig, so 10 gigabit base T, 10 gigabit Ethernet. So the other one you'll see, so again, it's 10,000 megabits. Cat 6 or 7, 6 is generally effective. There's another speed that's out there that's kind of weird because some of this cabling can't run 10 gigabits that long. We've come out with another standard called 2.5. So it's 2.5 gigabits. So it's a quarter as fast as the gigabit Ethernet, but it's also 2.5 times faster than the 1,000 meg per second. So you may also see 2.5 on some of those. And here's where I get dangerous. Before I came to Peru, this was my life. I lived in fiber optic cables. So altogether, I think I've been in charge of about 30,000 route miles of fiber optic cables in the United States. That's actually how I landed in this area, is we were actually installing fiber optic cables that actually come down the rail line and come out from, in this case, from Omaha to Kansas City in this segment. So fiber optics is how we do long-haul transmissions now. Previously, we did things with the coaxial cables. We did copper and a lot of retransmissions. Fiber optics allow us to push signal a lot further. So a fiber optic cable, if it's actual glass, and so there's some plastic ones also we use, but a core, and depending on the size of wavelength, that core can change, but it is smaller than a human hair piece of glass. And then they put a cladding around it, and that cladding is reflective on the inside, so that light signal essentially bounces down a hollow glass tube or a glass tube. So because that fiber is thin enough, it can bend, it can maneuver around a little bit. It's very, very small, and we can send data very quickly on it. Doesn't have electromagnetic reflections, So here, this is an example of fiber. And so they've blown this up a little bit, but if you see the red, that's the cladding, and then the fiber is actually the piece that's on the outside. So in most cases, this outside sheath has either, it used to have steel and now they have Kelvar threads in it to make it strong enough to withstand being used outside. So that cladding is what keeps that light in. So this sounds like it's expensive to make, and it is. But with the price of copper, it's actually coming down to very nearly equivalent costs. So why would we want to do it? It sounds like a pain. Well, if I want the fastest communication path possible, it's on fiber right now. If I don't want to be subjected to noise, I'm on fiber. If I want excellent security or great security, because I don't want the NSA to put a tap on my line, because the same way that those signals, we could lay something between them and pull up a signal, with wires, we could actually do that. You could steal a signal that way or tap into it. With fiber, I'm going to know if you tap into it. So, huge amount of data we can send, but it's more expensive, and we have to have special equipment. So the cutters and crimpers we have over here are about $10 a piece that we use inside the lab. For fiber optic, I've probably got $8,000 to $9,000 worth of equipment minimum to be able to actually make fiber optic connections. So we can reach tremendous speeds with fiber. I can go a long distance. So out here between Omaha and Kansas City, there's actually only one retransmitter. So that number, we've actually exceeded that by quite a bit, the 40,000 meters. So we don't have to retransmit as often. We don't have to have as much equipment to retransmit. Now, it depends on the cable and what wavelengths we're using and all kinds of things, but fiber optic gives us the longest run we can do. In a lot of cases, we can hit 80,000 or 80 miles, and we're still okay depending on our speed. And the way we get that is something called single mode fiber. So mode means what our frequency is, essentially. So laser sends a signal. It's matched very, very closely. So that cladding in the core, so we know that laser is very closely matched so that the wavelength just barely fits in there. So what we're trying to do is keep from something called dispersion. In other words, where it hits a wall and diffracts everywhere. So this is single mode. That's the most expensive. And so we're typically 8 to 10 microns. Somewhere around that range is what that glass is. Your human hair is about 70 to 80 microns. So if you think about that in terms of size. So it's very tiny. It's very precise. So that light doesn't go dispersing everywhere and lose energy. I want to think about it. The more times something bounces, think about a bouncy ball. The more it bounces, the more energy it loses. And that's the same way with light. So single mode, when we run between Omaha and Kansas City, or from Auburn to Lincoln, we're using single mode fiber. The other fiber that we're going to look at is something called multimode. And I want to show a picture of it first, because that multimode is gigantic in comparison when you look at it under a microscope. We're 50 to 60 to 70 microns, depending on what size. In some cases, we're even plastic, which doesn't let light go through nearly as easily. But for a short distance, it's pretty effective. But notice how that light bounces and scatters. So multimode means we can send all different kinds of signals in here, but we have that penalty of loss. So it's got greater loss than single mode, but for jumper cables from device to device or to a desktop or anything over a couple hundred feet, it's perfect. Works great, and it's cheap. It is cheap. So I will bring some fiber in that you guys can see some multimode, and they're super cheap. So there's all different kinds, just to make life miserable, there's all different kinds of connectors. Great. So this, for example, is what we call an ST connector. There's LCs, there's LTs, there's all different kinds of connectors. So you have to match the connector to your device, and you can order that fiber generally in any direction. The way we connect fibers, so this is a mechanical connection. So we've put them in together. We polish the end of that glass. So we hopefully don't lose a lot of signal at the going across from one to the other. The best way to connect them is actually called fusion splicing. So we're actually melting those little glass fibers together so it becomes one fiber. And we lose the least amount of signal at those. So think about when you've got a glass in front of you and it's got water in it, a real glass, and you put a straw in it. You see through the edge that it looks like that straw bends. That's that idea of diffraction, that it's moving that light a little bit. So you're going to see that we have a ton of different connections. So I'll show you some of the newer styles that we're going to get to.